Zeal Education Society, redefining excellence.
Hello, good morning to everyone. Myself Dr. Mahadev Unde, Professor in Electrical Engineering, Zeal College of Engineering and Research, Pune. In a previous video lecture, we have started the voltage regulation of alternator by EMF method, that is by conducting open circuit test, short circuit test and the resistance measurement test. And we have obtained the armature winding parameters like the armature winding resistance, synchronous reactance and the synchronous impedance by using this test. We will continue the test in this video lecture in order to find the voltage regulation by EMF method. Here it is how to find this open circuit or no load voltage per phase by using the various methods or by drawing the phasor diagrams for a lagging power factor, leading power factor and unity power factor. Now the first step is to calculate the full load current and the voltage drops. Now the full load current is given by IA equal to kVA rating of the alternator, kVA into 10⁻³ divided by √3 into VL. In this way you can calculate the full load current. If it is given in MVA rating, then MVA into 10⁶ you have to do. Then armature resistance voltage drop, IARA. Then similarly find out synchronous reactance voltage drop, IAXS. Then no load voltage per phase, E0 equal to EPH equal to VPH plus IHZS. In this way you can find out no load voltage per phase. But this is it is a phasor sum and not a arithmetic sum. So you cannot go directly by arithmetic here. And then you can find out the voltage regulation of alternator equal to E0. E0 is nothing but EPH minus VPH upon VPH into 100. Okay. So now we will start for the phasor diagram of a lagging power factor. At a lagging power factor, here the generated EMF P0 is greater than VPH. Okay. Now how to draw this phasor diagram at a lagging power factor? First of all, draw the OIA as a current phasor as a reference. Current phasor as a reference. Then draw the VPH such a way that the current will lag by an angle phi. Such a way that current is lagging the voltage by an angle phi. Okay, so OA represent the VPH. Then add the IARA drop parallel with the current phasor. IARA voltage drop parallel with the current phasor, and BC represent IAXS voltage drop which is drawn perpendicular to the current phasor. So join OC, that will give the E0, that is the no load voltage per phase. Okay. Then remember that, see this E0, you can observe by eyes, E0 is quite greater than the VPH. See here it is mentioned, and therefore voltage regulation is positive. Now here from the point A, the projection is shown at a dash, point B, the projection is shown at the B dash. Okay, as this is VPH and this angle is phi, it is known to us. Then we can find out the OA dash. OA dash is nothing but VPH cos phi. And AA dash is nothing but VPH sin phi. AA dash is nothing but BB dash, and BB dash is equal to VPH sin phi. Okay, and this AB equal to IARA, and that is equal to A dash B dash. Now by using the triangle OB dash C, OB dash C means by using the Pythagoras theorem. Okay. Now what is E0? This E0 is square root of OA dash plus A dash B dash bracket square plus B dash B plus BC bracket square. Okay. Then therefore this E0 equal to square root of what is OA dash, that is VPH cos phi, plus IARA bracket square plus this BB dash is nothing but VPH sin phi plus BC is IAXS bracket square. So in this way we can calculate E0. If required you can find out tan psi also, where psi is the angle phi plus or minus delta, angle plus or phi plus or minus delta. This plus or minus. Plus sign is for the synchronous generator and minus sign is for synchronous motor. Okay. And remember one thing is, okay, so therefore once you have obtained the E0, you can find out the voltage regulation, and voltage regulation is nothing but E0, this value which we have obtained by calculations by using this formula. By using this formula we have obtained E0, and VPH is known to us because it is given to us, and divided by VPH into 100. In this way you can find out the voltage regulation. As E0 is greater than VPH, numerator is positive and therefore voltage regulation is positive. Okay. So and one more thing is, note that as far as the synchronous generator is concerned, E0 always lead the VPH by an angle delta. See, E0 always lead the VPH by an angle delta for the generator, and E0 lags behind the VPH by an angle delta in case of motor. Okay, in this way the phasor diagram on lagging power factor is over, and we have observed that during the lagging power factor voltage regulation is positive because E0 is greater than VPH. Now come to the phasor diagram at a lagging power factor. The sin psi is here VPH sin phi plus IAXS divided by E0. You can find out cos psi also. But see, these are the values for the cylindrical rotor machine. In case of salient pole machine, you have to replace XS by XQ, where XQ is the quadrature axis reactance. Okay. In case of tan psi also, we have to replace the XS by XQ. Okay. So psi equal to phi plus or minus delta, plus the sign is used for the synchronous generator and minus sign is for the synchronous motor. Okay. So that same thing which I have explained is written here. Okay. So let us turn to the phasor diagram on a leading power factor. In case of leading power factor, what is given? E0 is less than VPH. Already we have observed it. Let us draw the OI as a current reference phasor. Current as a reference phasor. OI. Current as a reference phasor. Then see, draw the VPH such a way that current is leading the voltage by an angle phi. Such a way that current is leading the voltage by an angle phi. Okay. So OA represent VPH. Okay. Then add IA array drop parallel to the current phasor. IA array drop parallel to the current phasor. Then add the IA exit drop perpendicular to the current phasor, that is BC, and then join OC. Then join OC and B dash C. This triangle O B dash C is important as far as the voltage is concerned. This E0 is concerned. And if you observe carefully, in case of leading power factor, this E0, the value of E0, the magnitude of E0 is less than VPH by observation also. And furthermore thing is, this E0 leads the VPH by an angle delta because this is a generator. Now how to find, see, E0 equal to, observe the triangle O B dash C, O B dash C, okay, E0 equal to square root of OA dash plus A dash B dash bracket square, OA dash plus A dash B dash bracket square, plus BB dash, this is BB dash minus BC. You will get this magenta, this brown color triangle is important. We have to find out this one. So BB dash minus BC bracket square. So what is OA dash? OA dash is nothing but VPH cos phi. This is VPH cos phi plus this is IARA bracket square, because this A dash B dash is nothing but AB. Okay, and this A dash is nothing but VPH sin phi and this is nothing but BB dash. So it is VPH sin phi minus this IAXA bracket square. Okay, in this way you can calculate the E0 for a leading power factor. Therefore percentage voltage regulation is E0 minus VPH upon VPH into 100. Now in case of leading power factor, as this E0 is less than VPH, the numerator is negative and therefore voltage regulation is negative for a leading power factor. Okay. Now consider the phasor diagram for a unity power factor. Unity power factor also E0 is greater than VPH. Now draw the current phasor, OB as a current phasor. Then VPH will be on the same line because at a unity power factor the angle between current and voltage is 0. Angle between voltage and current is 0. They are on the same line. Then add the IARA, that is AB. AB as a IRA, voltage drop, in phase with the current, then add the IA excess, voltage drop perpendicular to the current, that represent BC. BC represent IA excess. Then join OC represent the E0, that is no load voltage per phase. And if you observe carefully, this OC, that is E0, is quite greater than the OA, that is VPH. And that's why it is written here. Okay. Now how to obtain? This is simple. By using the Pythagoras theorem also you can obtain this one. So it is OB square plus BC square, square root of OB. OB is nothing but VPH plus IRA bracket square plus BC square is IAXA bracket square. So in this way you can find out E0, and thus we can find out the voltage regulation E0 minus VPH upon VPH into 100. Okay, as E0 is greater than VPH, voltage regulation is positive. In general, what we can write, see, if you observe carefully, for lagging and leading, the formula for E0 is almost same except that this symbol, plus minus. This positive sign is for the lagging power factor and negative sign for the leading power factor. In fact, you can use the same formula except this change, and where positive sign is for the lagging power factor and negative for leading power factor. For unity power factor, put cos phi equal to 1. Put cos phi equal to 1, you will get VPH only. And put VPH plus IARA, and put sin phi equal to 0. If you put sin phi equal to 0, you will remain IAXS only. Okay. So in this way, we can obtain, or before that, see the tan delta. Here, what is the tan delta? Tan delta is nothing but IAXS divided by VPH plus IARA. This is for the cylindrical rotor machine, and in case of salient pole machine, you have to replace this excess by XQ, where XQ is the quadrature axis reactance. Okay. Now see the phasor diagram of a cylindrical rotor generator with RA equal to 0. For a large machines, generally the rating of the machine is more than 10 MVA, the RA is neglected. And for a lagging power factor, if the RA is neglected, how to find the phasor diagram? Now pay attention. Here I have taken OA as a voltage phasor, and draw the current lagging the voltage by an angle phi. If you observe carefully, OA is the VPH and voltage per phase. OA, VPH, voltage per phase. Then AC, we have to draw the AC, IA axis, voltage drop across the synchronous reactance, drawn perpendicular to the current phasor. See, this is the current phasor. You have to draw this BC perpendicular to the current phasor. See, here it is 90 degree. Okay. Then this magenta color triangle is important. Then join the OC. OC represent E0. Okay. So E0 is no load voltage per phase. Delta is the power. Delta is known as power angle or a load angle or a torque angle. Then observe carefully, this E0 is greater than VPH because of lagging power factor. One more point is E0 leads the VPH by an angle delta because of the synchronous generator, and phi is the angle between, this is the power factor angle between the voltage and current. Okay. Then how to find this E0? You can use either Pythagoras theorem or you can use the triangle rule. Means sides, these two sides of the triangles are known to us. VPH and IA axis is known to you. You can find out E0, and I would like to suggest use this formula only because that will be useful to you during the MMF method and Pottier method. Now the tan delta equal to, here also you can use the tan delta formula. The tan delta is nothing but IA axis cos phi divided by VPH plus IA axis sin phi. This is for cylindrical rotor machine. In case of salient pole machine, replace the excess synchronous reactance by the quadrature axis reactance XQ in both here and here also. Okay. So E0 equal to, see how to find the E0 by triangle rule. See these two sides OA and AC is known to you. How to find OC? So this OA is nothing but VPH and AC is nothing but IAXS square. So VPH square plus IAXS square, the square of these two sides, minus 2 times VPH into IAXS into cosine of angle between them. I will repeat it once again. Square root of VPH square plus IAXS square minus 2 times VPH IA axis into cosine of angle between phi pH and IA axis. Okay, and in this way we can find out E0, and once you got the E0, you can find out the voltage regulation. Okay. Now see effect of load power factor on alternator voltage regulation. What we have observed till now, this EPH and during the lagging power factor is greater than EPH during the unit power factor, and that is further greater than EPH for a leading power factor. Okay, and because of this relation, you will find that voltage regulation at lagging power factor is greater than voltage regulation at unity power factor is greater than voltage regulation at leading power factor. Therefore, for example, if the voltage regulations are 32%, 10%, minus 12% and 0%, comment on load power factor. As see, voltage regulation is positive for both the cases. Here it is and higher at the voltage regulation is higher for a lagging power factor. So 32 it is a lagging power factor, 10 it is a unity power factor. Both are positive. Both are positive for a unity power factor and lagging power factor. However, during this for a lagging power factor, voltage regulation is higher as compared to unity power factor. Observe this relation. And negative regulation is for the leading power factor. I have already stated zero regulation is possible for the leading power factor. So for both of these 0 and minus 12, it is a leading power factor. Okay, let us have another example also. See, if the voltage regulation are 25% and 15%, comment on the load. Here both the regulations are positive, indicate that the load must be either lagging power factor and unity power factor. But for the lagging power factor, voltage regulation is greater, and therefore for 25% it must be a lagging power factor and 15% must be unity power factor. Okay, so in this way we have finished this today's lecture. We will stop here and in the next video lecture we will learn the MMF method of finding the voltage regulation. Remember that the voltage regulation obtained by this method, that is synchronous impedance method, is little bit greater than the actual value, and thus it is stated as a pessimistic results. The results obtained are the pessimistic, means somewhat inferior, means the values are little bit higher than the actual values because of the impedance which we have considered there. This is the reason. Okay, and in the next lecture we will see the MMF method. Thank you.